Hi guys, welcome to the last day of class. Thank you for sticking it out with me for the whole semester. I know it's been a bit of an odd semester. Today we were just planning on doing some exam review, but before we did that, I wanted to talk a little bit about, what you should be doing to prep for the final exam and to see if you guys had any questions. So sort of my thoughts on the final exam are, kind of what I would do is can you guys hear me? Oh, okay. For some reason there's a muted symbol on my screen. So what I would do for the final exam is I would probably do a very basic review to get started. Maybe put together the list of all the, formulas and ideas that I might need. And then I would try the practice exam under sort of timed conditions. And, because that's a good way to gauge what things are your weaknesses, which things are your strengths, what do you need to work on. And then go back, study some of those things, and then maybe do the other practice exam that's maybe in the study guide I sent out. And then if you have extra time, go back and look at summary sheet questions, web assigned questions, old exams, old quizzes, those sorts of things. So in my mind, that's sort of how I would approach it. And mostly what you're looking for is just to get in as much practice as you can, and preferably new problems. Going back and looking at how you did old problems is fine, but you also want to make sure you keep doing new problems so you don't kind of stagnate. All right, so do you guys have any questions before we just, jump right into things? So there's a question about whether it will work just like a normal test. So the logistics of the final exam will essentially be that it'll work basically just like one of our midterms, except it'll be 3 hours instead of 2 hours. So the things you should maybe worry a little bit about it are I am going to be more strict with the timing. So please make sure you're getting it in on time. I'm just trying to make it as fair for everybody. And if you're taking extra time, it can be a little unfair to other people. Do stop the exam, preferably 15 minutes ahead of time so that you have enough time to scan everything, verify that it's all in your file, and then upload it. Okay, but yeah, other than that, it will work exactly like a normal test. It will be almost all open answer questions, which you can get partial credit on, and it's cumulative. Okay, so other questions? So what percent of the exam will be material from after exam 3? So kind of what you should expect is sort of one question per section. There isn't quite that much, but that's roughly what you should expect. So I don't know what that works out to be, maybe 10%, something like that. So they will be on there, like one question in each type. That's kind of essentially how it works usually. Ready? Okay, well, let's just jump right into today then. The announcements for today, there aren't that many, just a couple of reminders. The final exam, which we were just talking about, is Monday, May 4th. (9 a.m. to noon). And the other thing is you have your last homework due tonight. And again, you should verify that all your grades are correct in Sakai. Just so that I don't have any issues when I'm calculating final grades. And maybe it's good news for you guys. I'll just tell you now. On the last quiz, there was a bit of a typo, kind of a major typo that made it worth not grading. I had intended to give you the velocity function, but on the quiz I wrote position function, and it changed the function changed the answer quite drastically. In some sense, it made it easier, but it was also more confusing. So I decided I'll just post solutions and give everybody a 10 out of 10 because it was sort of my fault. So, you can take that as sort of a gift from me to you as your end of semester here. All right. Okay, so that's everything on my mind. Any other questions before we go to math? Today we're just going to do a bunch of review. Okay. So yeah, let's jump right into some of these. Where did it go? So I thought we'd start with some old material first and then kind of work our way up to the newer stuff. Though we might jump around a little. We're certainly not going to get to all the problems we have here, and I will post the complete thing with the solutions after class. But so what I want you to do today is, for each question, I want you to take 1 minute and just plan what you would do to answer the question. Like, don't actually do it, but just make a plan, because having a good plan of how to approach problems is it's worth its weight in gold on exams, at least. And in general, like having just an idea of how to approach things is sort of a good idea. So I want you to take 1 minute, read this problem, and plan what you would do to solve it. And then I'll go through it. Okay. So the way I would approach this is we're trying to determine basically where this function is continuous or discontinuous, right? And so whenever you have a piecewise function, you know, a piecewise function basically says, you know, you have a function, what's the best way to say that? Is I would first look at each piece individually. So I'd look at this first piece. So where is this continuous? And this is one of those ones that's continuous on its domain. And so the answer is, well, maybe let's write it down more properly down here. So x squared plus 3x on its domain, and its domain is everything where the denominator is not 0, right? Because that's the only thing that could cause this to be undefined. So its domain is x not equal to 1, or in interval notation, that would be everything but 1. And but where is this function living on over the x-axis? So it's for x less than 3. So 3 is over here somewhere. Then we have 1 in here somewhere. And those are the basic values that show up here, right? 3 and 1. And so it says this function, this is what the function is everywhere except at 1. And so what we know about this function is, well, if I plug in 1, what do I get into this? So we would get 1 plus 3 minus 4 over 1, or sorry, over 0, which is 0 over 0, right? So that indicates basically nothing. It indicates that there could be a vertical asymptote or there maybe isn't. And to determine which, we should look at the limit. So let's look at the limit as x approaches 1. And so this is one of those ones where, because we got 0 over 0, we want to do some sort of cancellation, do some algebra, get something to cancel. And we factor here. So let's see, what does this factor as? It's got to be what, minus 4 and positive 1. No, the other way. Minus 1 and positive 4, there we go. So it's the limit of that over x minus 1, and we see that the x minus 1s can cancel, right? X goes to 1 of x plus 4. And now, because there's no division by 0, I can just plug in, and this is just 5. Okay. So essentially what we just determined is that even though this function, or this function that I'm highlighting in yellow, even though it has a division by 0 at 1, it still has a two-sided limit there. So this means that was a removable discontinuity there. So sort of in our picture, you know, maybe we don't know exactly what this function looks like, but what we know is that we know it's continuous everywhere except for 3, or sorry, except for 1. And we know there's a hole at 1 because it's a removable discontinuity, and we know it does something else up till 3. But it's continuous between 1 and 3 as well. And then I might look at this last part. Well, we know a polynomial is just continuous everywhere. But the problem is, because that's a different equation, we have to ask ourselves, does it do something like, so let's see, this side's filled in. Does it do something like this? Or does it do something like where they actually match? Like, we don't know which of these two pictures it is. Maybe I should draw them in a different color because we're not certain. Like, it could be a situation where there's a jump here, or it could be that they actually match, right? So we're trying to decide which of these it is. And then the other part we haven't used is at x equals 5. Well, that looks like a familiar number, right? Down here, we decided that the removable discontinuity should have been filled in with 5. And so by making the function equal to 5 there, what we've done is we've just completed the graph there by filling in that removable discontinuity. Okay, so we know it's now continuous up till 3. Now we just have to decide what happens at 3. Is there a jump or is there not? And the way we do that, so what happens at 3? To determine that, we're going to look at the two one-sided limits. So if we come from the left at 3, we're going to compare that to the limit from the right. And if they're equal, then there's no jump. If they're different, then there is a jump. Okay. So remember, a limit, either one-sided or two-sided, doesn't care about the value at 3. And so let's get rid of all these circles and underlines. So to the right of 3, for x bigger than 3, that means to the right of 3, I have this formula. So if I'm approaching from the right, I only care about what happens to the right. So this is the same as 2x squared minus 11. And that's something we can just plug in, right? We're basically asking, like, if we approach from the left and the right, do we end up with the same thing? So this will be 18 minus 11, that's 7. If we approach from the left, that would be for x smaller than 3. So that's this first formula. So what was that? That was x squared. And that we can just plug in, presumably. So we get 9 plus 9 minus 4 over 2. 18 minus 4, 14. So that looks like a 7. So there's no discontinuity here. Though we should be careful. Yeah, I got ahead of myself here. I didn't read this closely enough, but so what I'm saying here is not strictly true. So if we wanted to draw the graph from what we've just learned, what we would realize is that if I approach from the left or from the right, I get the same number. But we could have kind of skipped that even, because if you look very carefully at what this function, nowhere in here does it say what happens at 3. So if a function's undefined, it's automatically not continuous there, right? It has to have a value if it's continuous. So this is what the picture would look like, though, if you did graph it. Okay, and so then your answer would be that you know, we kind of showed the work of why it's true, but it's only, f is only discontinuous at 3. Okay. Okay, so questions about that one. It was a little bit more of a conceptual problem. Okay. Let's jump to another graphing one. So this one, I think I'm just gonna, well, no, take a minute and try to do this one. This one should be quick enough that you don't have to actually plan it out. But I go ahead and give this one a try and see where you get to. I'll give you a minute and then we'll go through it together. Okay. So in this one, we're asked to basically make up a function. There's many functions that would have all these properties, but we're going to just try to draw the graph of one. So let's draw a graph here. Okay, so what do we know about it? So we have some domain. It's open on the left, so 5 will be over here somewhere, and minus 6 will be over here. That's supposed to be our domain. And then what other special points are there? There's something happens at 0, another thing happens at 0, something happens at 2, something happens at 5, and something happens at minus 6. So that means we kind of need 2 points in the middle here. We have 0, that one, and then we have 2. Something happens at 2. Okay, so then maybe we look at the first one. So it says f of 0 is 1. So that means we know a single point on the graph, where this is the number 1. Then the second thing says the derivative at 0 is 0. So that means, kind of nearby it looks pretty flat. It could be like a local min or a local max or something else. We have to decide what we want in a second. Then we have this weird condition that f of prime of 2 doesn't exist. So maybe we'll come back to that one. Then what do we have here? So this says if we approach 5 from the left, we should get a 4. And because this is closed, so 4 will be up here somewhere maybe. Okay, and so we know that as we approach from the left, we should approach this point 4. This should be 5 comma 4. Something weird happens at 2. We know that there should be a 0 derivative at 1, and then our last condition. So this one's done, this one's done, this one's done. Is as we approach -6 from the right, we should get a limit of plus infinity, which means it basically has a vertical asymptote there. So there's a vertical asymptote here, and the graph has to go up. Okay, and then we just try to figure out what's a way to make all these things happen. How do we link them? Well, we weren't really given any other things that needed to happen between 0 and 1, except that it has to be continuous, so that just means it's an unbroken line. So maybe we make it look like a local max, local min here, maybe. So, as a first guess, we might try something like this. Or, if we wanted to make it look even a little better, we could do something to make it more clear. You could do something like, make it look like that. Okay, but there's one thing we haven't checked yet. That f prime of 2 doesn't exist. So what does a picture look like for a function that has a place where it's continuous but not differentiable? And so if you remember, the usual way that happens, or the easiest way it can happen, is if there's some sort of kink or cusp. So maybe you have like, let's try that again. So maybe you have a point and then it makes a sharp angle change. And then the rest of it is smooth. So something like this. There are many pictures that would work here, but this would be one of them. Okay. So questions about that one? Okay, well, let's go back to thinking about this section. It's been a while since we did this. So this is implicit differentiation. So take 1 minute and try to remember the plan of how you approach these problems, and then we'll go through it. Okay. So in these problems, the trick is to, when you have an equation where it's difficult to solve for the variable in which you would like to know the derivative of, so here y, we can do it implicitly by treating y as a function of x. So basically the idea is we're imagining that, y is some function of x, right? There's some formula, like it could be x to the 3 over 1200. There could be some complicated formula for y that we don't want to actually solve for, or we can't. But we imagine that we could, and so we just give it the name like y of x. And then once we've done that, then we differentiate both sides. With respect to x. So here that would look like and then when we do that, so the first one would just be 8x cubed. Then you'd get 8y cubed. But then you have the chain rule, because the derivative of, whenever you're doing this, you could think of like the first one, you could think of this times dx. But this is just 1. So we usually don't write it, right? So there, you can always use the chain rule there, but we don't usually. And but when you do it with the y does have some derivative because of the way we're treating it. So it'd be 8y cubed, and then you have an extra derivative of y with respect to x from the chain rule. And when you're doing these implicit differentiation things, whenever you have a derivative of, in this case y, you would expect to have a dy dx appear somewhere. The other side is 0. And you have two options here. You could either solve for dy dx, but here we're looking for y double prime, second derivative. So I'm just going to go ahead and take another derivative here. You could solve for dy dx and then take the derivative again, but it amounts to the same sort of thing, and I think it's easier this way. So the derivative of 0, which will just be 0. And so what do you end up with? You end up with 24x squared. Okay, so now here you have a chain rule, right? Because you have two functions multiplied. So you're going to get a 24y squared, derivative of the first one, plus, now you leave the first part alone, and then you take the derivative of the second part, and the derivative of dy dx is just the second derivative of y, which, you could use this notation. And then you would solve for dy dx, or dy squared, d squared y dx squared, which will be minus 24x squared minus 24y squared dy dx, divided by 8y cubed if you do all the algebra. But this is still a little unfortunate because we have this extra dy dx hanging around. So how do we solve that? Well, we would have to go back up to this equation and solve for dy dx. That's usually the easiest way. So that's the same as minus x cubed over y cubed. And so we could replace that in here. And this would be your answer. Okay, so questions about that one? All right, let's try another one. Okay. So take a minute on this one. Remember what the limit definition of the derivative is, and see if you can write down at least the first step of it. And then think about how you would approach the other parts. So take a minute and I'll go through it after that. Alrighty. So yeah, let's remember that the limit definition says, it just is the definition. We typically call it the limit definition. Is the limit as h goes to 0 of f of x plus h minus f of x all over just h. Okay, so we try to write that down for this function, and it would be f prime of x will be the limit as h goes to 0, and now the first term will be 3 times x plus h squared minus 2 times x plus h plus 4. That's f of x plus h. Then f of x is just exactly f of x, all divided by h. So it's a little bit long, but it's not that bad. Then if we expand everything, so the first term will be, let's drop all the parentheses when we can, 3x squared plus 6xh is 3h squared minus 2x minus 2h plus 4 minus 3x squared plus 2x minus 4. So you get this long mess, but the point is a lot of it cancels, right? 3x squared cancels with negative 3x squared, or they subtract to be 0. Then we have negative 2x and positive 2x. Then we have 4 and negative 4. So after that, there isn't that much left. So what's left after that is, let's see, 6xh plus 3h squared minus 2h all over h. And the point here is that all these terms contain an h, right? So if I want to pull out an h, I can take an h out of everything. And I'm left with like this. And the h's cancel, right? That's usually the goal of these problems, is to get the h to cancel out of the denominator, in a correct way at least. Okay, so then we're just left with limit of 6x plus 3h minus 2. And now, since there's no division by 2, we can just plug in for h. Plug in h equals 0, and we're left with 6x minus 2. Right, and if you just go back and check, like we know the derivative rules now, so we can check that easily that the derivative of f should be 6x minus 2, right? So we did get the right answer. Okay, so questions about that part? So the next part of this question is asking, which point on the graph of f is the tangent line parallel? So the key word here is parallel to this other line. So parallel will mean has the same slope. So it's asking which point on the graph of f has the same slope as this line. So this line, well, maybe it's easier to see if you rearrange it. If you put the 10 on the other side, right, this is 10x plus 2, has slope 10. And so the question then is, we're asking for which x is the derivative of f, so that's f prime of x, when is that equal to 10? For which x value? But we know the derivative is 6x minus 2, so we get 10. Do a little algebra, you get 6x equals 12, x equals 2. But they asked for a point. So f of 2 is what? It's 4, 12 minus 4 plus 4. So the point is 2 comma 12. Okay, so I was just sort of interpreting the question and writing down the equation that tells you what you want to know. And then the last question is to write an equation of the tangent line. Right, so remember, for a line, at least in my opinion, the easiest way to do it in these circumstances is to find a point that's on the line. And so our point is exactly the one we just found. And then we want the slope of the line. So the slope we found had to be 10, right? We knew that at this point the slope was 10, right? That's what we solved for. Okay, and then there's point slope form of a line, right? So it's whatever way you want to remember it. I typically remember it like this, where my point is x naught, y naught, right? The subscripts usually mean they stand for numbers, and no subscripts means a variable. Not all the time, but in this case. And so if we do that, we would get y minus y naught is 12, right? This is y naught, this is x naught. Slope is 10, x minus 2. And a lot of times we would probably write this with the I would probably end up writing it like this in the end. Okay, so questions about this one? Let's do a linearization one next. So take a minute and try to plan how you do this one. Okay. It's getting windy here. So let's see. So when we're doing a linearization problem, usually the first things we have to decide are, what function to use and which value to linearize at. And here they're given to us. Though in this, there's always multiple ways you can do it. But first of all, you would remember that the linearization formula is essentially just the formula for the tangent line, which is like this. So I guess here we're using A, not C. It's the place that you're linearizing at. And so we need to figure out all these things. So f prime of x is 1 over 2 square root of x plus 15 times the derivative of x plus 15, but that's just 1. And then f of a, it'll be the square root of 16, which is 4. So L of x, sorry, so this should have an a in it. Right? The slope should always be a number. Right? If you have a slope that involves x's or variables, it means something's gone wrong, or you didn't plug in. So I guess we also need that. F prime of 4 is 1 over 8. Sorry, f prime of 1, but still 8. Plus 4. Okay, so that would be your first step, is you find the linearization at a value near to something that when you plug it in gives you the answer, right? So something near to 16.05 is 16, and plugging a equals 1 in gives 16, right? So that's sort of why they chose a equals 1. And then the next thing is to recognize that square root of 16.05 that's just the same as f of 16.05. And we can approximate that because it's close to, or sorry, that's f of 1.05, right? Because if I plug 1.05 in for x, I get 16.05. And because 1.05 is close to 1, we can use the tangent line instead of the function itself and still be fairly close. So that's the approximating part. And then we just plug it into this. So it's 1/8. So it's 0.05 over 8. So whatever that works out to be. I wouldn't worry too much about wasting your time simplifying these things, right? Be smart about how you use your time. But questions about that one? So we only have like 15 minutes left. Do you guys want to see this graphing one? Or we could jump over and do some integral ones, some of the newer stuff. Which would you guys prefer? You guys don't really have any preference? Okay, well, we'll do the graphing one since it's here then. There's another part to this review that I'll post solutions to you can look at. So typically the way I approach these graphing problems is I sort of gave you some guidelines, but kind of the way I remember it is I kind of first figure out what the skeleton of the graph looks like by figuring out what the asymptotes are. So the asymptotes, so there will be no slant asymptotes because the degrees are not the right here, right? The top and bottom both have degree 2. Whereas for a slant, the top has to be exactly 1 degree higher. For horizontal asymptotes, that comes from asking what happens as the limit goes to infinity of something like this. And if you remember, because these both have degree 2, it'll be the ratio of their coefficients here, so that'll just be 2. But right, when we talk about asymptotes, you got to remember that you want to write that as a equation, right? So this is y equals 2. And then for vertical asymptotes, that's basically where the denominator is 0 and the numerator is not 0. So that'll be when, so you get 2 of them, x equals 5 and x equals minus 5. Okay, so we have three asymptotes here. Let's see. So we can start putting a graph together. Let's make that black. Okay, so we said y equals 2. So maybe up here somewhere. And then we had vertical ones at plus or minus 5. Sorry, these are x equals minus 5. And then one roughly the same distance on the other side. Okay, so those are the asymptotes. The next thing I would do is I would analyze the first derivative. So let's see what the first derivative is here. So the first derivative is given to us, which is nice. So it's minus 100x over, so I'll just copy that down here. This. And remember, we're essentially looking for where is this positive and where is this negative to help us identify, increasing, decreasing, and local minimums and maximums. So we ask ourselves, where is this 0? And the answer is only when the denominator is 0. So we get 1 point. And then we make a number line. And we put our critical value, but we also have to put the vertical asymptotes on there. So we should also put minus 5, and we should also put 5. And then we test a point in each region to determine the sign of f prime, right? And one thing you can notice is that the denominator is always positive. So it only matters what the sign of the top is, right? And so for negative numbers, it will be positive. So here we get positive, it'll be positive here, and then negative, negative. Okay. So that means, these two are asymptotes, so they couldn't have been anything anyways. But that means at 0, it went local max here. And so if we have a local max, what I would do is I would go ahead and I'd figure out what that value is. So what's f of 0? Is it actually 0? I think it is. It's just 0. Okay. So that means our local max is at 0, 0. And we can go put that on our graph, right? So it means there's a local max at the origin. And we know, like, nearby a local max, it'll have to do something like this, roughly, right? Okay. Then the next thing I would do is I'd go and analyze the second derivative in just exactly the same way. So what was the second derivative? It was a slightly uglier thing, 100, 3x squared plus. Let's double check that that's right. Yep. And I put a cubed, right? No, I didn't. Okay, so that's the second derivative. And again, we want to figure out where is this positive or negative, so we might first figure out where it crosses through 0. And that would tell you that the top has to be 0. I don't want this one. And you'll quickly realize, like, you know, if you try to actually work this out, you can do a little algebra and get to the fact, like, you have, like the left-hand side here has to be positive and the right-hand side has to be negative, right? So there's no solutions here. Okay, so there's no places where the second derivative is 0, but we still have to do the number line thing, and the asymptotes still have to go on the number line because there's still places that any of the derivatives could switch. Okay. And now here what we can notice is that the numerator is always positive because of the squared, and then we're just adding and multiplying by positive stuff. So then we only have to worry about the bottom. So if I plug in something like 10, I'll get like 100 minus 25 cubed. That'll be a positive number. So maybe I choose like 10 over here. Maybe I choose like 0 in here. If I plug 0 in to the denominator, it will be negative 25 cubed. And if I cube a negative number, it's still negative. And then if I plug like negative 10 in here, well, because I'm squaring it, it'll be the same as plugging 10 in, so it's going to be plus again. Okay. So there's no inflection points here, but we do know that it has to go concave up, concave down, concave up. And then it should be increasing, increasing, decreasing, decreasing. Right, so what did we say? We said concave up and increasing. So that to the left of minus 5, it has to be concave up and increasing, and it has to, so because it's increasing, it has to approach the asymptote going up from the right, which means to be concave up, it better do something like this. It has to approach the horizontal asymptote as it goes to the left as well. Okay, then in the middle, it's, so in this region, it's concave, or sorry, it's increasing and concave down. So that because it's increasing, it's going to have to, you know, approach this asymptote somehow. So maybe something like that. And then if you check the rest of it, you'll see that it has to go like this. Not the best drawing, but, and then here it'll go like this. Now, let's just double check that one. It should be decreasing. Right, that part was decreasing and concave up, which matches, right? So that's roughly how I approach these things: is find the asymptotes, analyze the first derivative, analyze the second derivative, and then try to glue it all together. Okay, so questions about that one? Okay, well, I think I'm going to let you go there then. I think there's only 5 minutes left. I did have a bunch of other integral ones put together as well, but I'll just post solutions to that, and you can look at them if you want to, or if not, you don't have to, but yeah, thanks for a great semester, and good luck with your futures and on the exam.